Section 5.5, satellites in circular orbits. So if you have a satellite, it turns out there's only one speed it can have for the satellites to remain in orbit with a fixed radius, right, at a single circular path. And we can calculate that speed using our knowledge of Newton's second law and the force that is keeping it in that circular motion, which in this case is the gravitational force pulling down on the satellite, pulling it towards the Earth as it moves perpendicularly to that pole. So if we go back to Newton's second law, remember the net force is equal to the mass times the acceleration. That's what we have here at the top. And we can say, hey, the net force acting on the satellite is just gravitational force. We're going to use our full one because we aren't near Earth's surface. We're outside of that. So G times the mass of the satellite times the mass of the Earth divided by r squared, where r is the distance from the center of the Earth to the satellite, right? That radius of its motion. That's our net force, and we want to set it equal to our mass times our centripetal acceleration, v squared over r, because since the satellite's moving in a circle, it has to have that centripetal acceleration. Now we notice this mass is going to be the mass of the object that we're drawing the free body diagram for, what the forces are acting on, so is the mass of the satellite. We have that on both sides, so that's going to cancel out. And we also can cancel one of our radii out, and then we can just take the square root, and that will give us the speed that our satellite needs to stay in a circular orbit. And that's the square root of g, our universal constant, times the mass of the Earth divided by our desired radius. Now this could apply for other massive objects than the Earth, but here we just have it in terms of the Earth. So let's look at an example again with the Earth. So orbital speed of the Hubble Space Telescope. So we want to determine the speed of the Hubble Space Telescope that is orbiting the Earth at a height of 598 kilometers above the Earth's surface. A couple notes here: Earth's mass and radius are 5.98 times 10 to the 24 kilograms and 6.38 times 10 to the 6 meters respectively. Right, so as we think about the equation on the last slide that we just saw, we know it involves the mass of the Earth. So we're glad that we have this mass of the Earth. That's something we can fill in right away. The other thing it involves to determine the speed, to get that v, is we need to know the radius. But notice they give us two different distances here. So what are we going to use for the radius? Well, remember the radius is the full distance from the center of the Earth out to the satellite. So that means we're going to need both the distance the satellite is from the Earth's surface as well as the radius of the Earth. Let's check it out in the calculation. So when we calculate v with the square root of g, I'll rewrite it, g times the mass of the Earth divided by the total radius r. Notice in the denominator, we are adding the radius of the Earth plus the additional distance above Earth's surface. And there is a unit conversion here. Because this was written in kilometers, that got converted to meters by multiplying by 10 to the 3, by multiplying by 1,000. So you want to be careful to do that and make sure to do that addition before you try to divide or use parentheses. And if you do that properly, you should get 7.56 times 10 to the 3rd meters per second. Or in other words, 16,900 miles per hour. Whew, that is fast. But satellites like this are really important. They have a number of applications. One such application is Global Positioning System, more commonly known as GPS. So Global Positioning System is able to send a signal down to a receiver, say in your car, and that receiver sends the signal back up. It can use that known distance and the delay in time to figure out that your car must be at a certain distance away from it. That only narrows down your position to a circle though. If you only have one GPS satellite, then it can know where you are on the outer edge of a circle because that's always at a constant distance from it, but that's about it. If you add in a second GPS satellite, then you have two circles that overlap at 2 points. And so you can narrow down the position to 2 possible points. If you have 3 GPS satellites, now it's where all 3 circles overlap, and so that will have to be a single point. And so that's one way that they can locate cars. In practice, there's also some ground-based systems that will help to verify and speed up the GPS process. Satellites also sometimes are designed to be geosynchronous, where they stay at the same point above the Earth at all times. This is really useful for communications, like if you have a digital satellite TV, right, where you want to get the signal from the satellite. And so in order to do that, we can set our desired period at 24 hours. And to get a period of 24 hours is going to be a very specific radius given the mass of the Earth, right, traveling at that specific speed. So you can set it just right to get that period properly. Just wanted to highlight that because it is pretty cool to see. And it turns out there are a lot of satellites now that are at that very specific radius because of that desired property. And it just goes back to physics because everything does.